Hello everybody. In this video we are going to be looking at the solutions to the honors refraction homework problems 1 through 5. Problem number 1. The speed of light in a certain substance is 89% of its value in water. What is the index of refraction of this substance? So I know that the speed of light in this substance is 89% of the speed in water, or 0.89 times the velocity of water. And I know that the index of refraction of water is 1.33. That is from the table that has all the indices of refraction in the PowerPoint. You could also Google it, or you can find that table that has the indices of refraction in the formula sheet that I have posted in the toolbox on the website. I know that the index of refraction is equal to the speed of light in a vacuum, c, divided by v, the speed of light in a medium. Solving that for v will give me the v equals c divided by n. So plugging in my known values for this, I know that 0.89 times the velocity, let me try that again, 0.89 times the velocity in water equals 0.89 times c divided by 1.33, and that equals c divided by n. So I can take this proportion, and basically this is all just a proportion problem, and solve for this n in this proportion. When I do that, the first thing I want to do is cross multiply, and when I cross multiply, I have 0.89 times c times n equals 1.33 times c. I can reduce this down and cancel c from both sides, and I get 0.89 times n equals 1.33. Dividing both sides by 0.89 will give me n equals 1.33 divided by 0.89. And I do that math out, and that will give me an index of refraction for this substance of 1.49. Problem number 2. A diver shines a flashlight upward from beneath the water at a 42.5 degree angle to the vertical. At what angle does light leave the water? So the light starts off in water and travels to air. So my incident medium is the water, my refractive medium is the air. My angle of incidence, which is theta 1, is equal to 42.5 degrees. My index of refraction for the water, which is N1, is 1.33. My index of refraction for air is 1.00. And I'm trying to solve for my angle of refraction, or theta 2. And remember, even though these are not explicitly given to you in the problem, you can find them on the table from the PowerPoint or from the formula sheet in the toolbox on the website. So I need to solve for theta 2. I'm going to start off with Snell's law. In solving for Snell's law, essentially what I'm going to want to do is divide both sides by n2, and when I do that, that will cancel out, but I still have a sine theta 2 on that side, so then I need to take the inverse sine of both sides, and when I do that, I will have theta 2 equals the inverse sine of n1 times sine theta 1 divided by n2. I plug all of my known values into that equation, and I am going to have an index, or an angle of refraction of 64.0 degrees. Problem 3. A light beam coming from an underwater spotlight exits the water at an angle of 66.0 degrees to the vertical. At what angle of incidence does it hit the air-water interface from below the surface? So in this case, we are given the angle of refraction, the angle at which the light wave leaves the water. Remember, we always measure these angles from the normal, which is perpendicular to the boundary, or the boundary between the two mediums. So in this case, we're going from water to air. I know that the boundary between the air and water is usually horizontal. If your water isn't horizontal, you got a problem. So my normal is going to be a vertical, imaginary vertical line, and it says that this is measured from the vertical. So my angle of refraction is 66.0 degrees. My index of refraction for my water is 1.33, and the index of refraction for the air is 1.00. And I'm trying to find my angle of incidence. So again, we're going to start off with Snell's law, but in this case, we are going to be solving for theta 1. So using all the same mathematical procedures as we did in the previous problem, solving for theta 1 will give me the inverse sine, theta 1 equals the inverse sine of n2 times sine theta 2 divided by n1. Plugging all of my known values into that equation will give me an angle of incidence of 43.4 degrees. Problem 4. Rays of the sun are seen to make a 31.0 degree angle to the vertical beneath the water. At what angle above the horizon is the sun? So we are given the angle of refraction of the ray of light into the water, and that is 31.0 degrees. The index of refraction for the air, which is N1, is going to be 1.00, and my index of refraction for water, N2, is 1.33. And we were trying to find the angle above the horizon, so that's why we're trying to find the angle above the horizon. So if I was to draw this in a really horrible picture, here is the water, here is the air, we have our sun up here, and remember, we have a very mean and angry sun because it gives us skin cancer. And so the ray of light is traveling here through from the sun to the water. Now we are measuring, or when we solve this for Snell's law, we are going to be solving for this angle right here, theta. But the angle that we're being asked to find in this problem is the angle above the horizon, or this angle. So once we find our angle of incidence, we have to then find this angle, which is just going to be the complementary angle. So let's take a look. We're going to start off again with Snell's law. We're going to solve Snell's law for theta 1, or my angle of incidence, this guy right here. And solving Snell's law for theta 1 is going to give me an angle of 43.2 degrees. Now to find the complementary angle of 43.2 degrees, I need to take 90 degrees and subtract my angle of incidence. So 90 degrees minus 43.2 degrees will give me an angle above the horizon of 46.8 degrees. Problem 5. An aquarium filled with water has a flat glass sides whose index of refraction is 1.52. A beam of light from outside the aquarium strikes the glass at a 43.5 degree angle to the perpendicular. What is the angle of this light ray when it enters A, the glass, and then B, the water? C, what would be the refracted angle if the ray entered the water directly? So what's happening here is that we have a ray of light that starts off in the air outside of the aquarium. That ray of light then hits the air glass boundary and it will refract into the glass. As it continues to go through the glass, it's then going to hit the glass water boundary and refract from the glass into the water. So the first thing we want to do is find the angle of refraction of the light ray into the glass. So my index of refraction for the air, which I'll call substance 1, is 1.00. My index of refraction for the glass, which is given, is 1.52, and we'll call that substance 2 and use a subscript 2 for glass. And then the index of refraction for water is 1.33, and I'll call the water substance 3 and give everything that deals with water a subscript of 3. So I know my angle of incidence from the air into the glass, or theta 1, is 43.5 degrees. So the first thing they want us to find is the angle of refraction as the light travels from the air into the glass. So that is going to be theta 2, and I am going to use a subscript r to note that that is my angle of refraction into the glass. So again, I know N1 is 1, N2 is 1.52. I'm going to use Snell's law to solve for theta 2 and the refracted angle into the glass. So solving for theta 2r is going to give me theta 2r equals the inverse sine of N1 sine theta 1 divided by N2. Plugging my known values into that equation will give me an angle of refraction into the glass of 26.9 degrees. Part B of problem 5 asks us to find the angle of refraction into the water. So both of the surfaces, or both sides of the glass, are parallel to one another, and because both of those interfaces are parallel to each other, I know that the angle of refraction from the air-glass boundary is going to be equal to the angle of incidence at the glass-water boundary. In other words, my angle of refraction into the glass is going to equal my angle of incidence from the glass into the water. And that is just the alternate interior angles that you guys know and love and remember from geometry. And why wouldn't you love alternate interior angles? And if I was just to draw that real quick, and not draw it well, obviously, because I can't draw very well, if I have my incident angle coming in here, and then I draw a normal for that, I'm going to have this light ray refracting into the water at some angle here. Now, as this continues to the air-water boundary, again, let me draw a normal to this boundary here. It's going to refract again, like so, and this is going to be my angle of incidence from the glass into the water. And this angle, because they're alternate interior angles, are going to be the same. So my angle of incidence in the glass, or going from the glass to the water, is going to equal my angle of refraction from the air into the glass, and that was 26.9 degrees. I know that my index of refraction for the glass is 1.52, and my index of refraction for the water is 1.33, and we are looking for the angle of refraction into the water, or theta 3. Once again, I'm going to be using Snell's law, but in this case, I'm going to be using subscripts 2 and 3 because I am dealing with the water and the water and the glass. So I want to solve this form of Snell's law for theta 3, and that will give me theta 3 equals the inverse sine of N2 sine theta 2 refracted divided by N3. Plugging my known values into that equation will give me an angle of 31.1 degrees. Part C asks, what would be the refracted angle if the ray entered the water directly? In other words, let's pretend that the glass isn't there. I don't know what's holding the water in place if there's no glass, but work with me, people. Work with me. So now we have the ray of light going from the air directly to the water, and we want to see what the angle of refraction going into the water would be in that case. So again, the index of refraction for the air is 1. My angle of incidence from the air into the water is still 43.5 degrees. My index of refraction for the water is 1.33. And I'm looking for the angle of refraction into the water, or theta 3. I'm still going to use Snell's law. I'm going to use the version of Snell's law that I'm going to compare substance 1 and substance 3. So I'm going to use those subscripts. And I want to solve for theta 3. So theta 3 is going to equal the inverse sine of N1 sine theta 1 divided by N3. I plug my known values for the index of refraction for the water, the angle of incidence, and the index of refraction for the air into that equation, and I'm going to get an angle of refraction of 31.1 0.1 degrees. And this, if you recall, and you should recall because it was just about a minute and a half ago, that is the same angle of refraction when the light had to go through the water, through the glass. And the reason for that is because the sides of the glass are parallel to one another. And because they're parallel to one another, they kind of cancel each other out. So theta 3, or my angle of refraction into the water, is independent of the ray of light having to travel through the glass, because both sides of the glass are parallel to one another.